Welcome to Mutual Information. My name is DJ. In this video, we're going to learn about Gaussian processes for machine learning. Now, personally, I think GPs are some of the coolest models out there. And you might have been able to guess that since they're on my computer. And they're there for good reason. Let me list a few. First, for most ML models, when you provide an input, you get a single number as a prediction. But GPs offer full distribution to reflect uncertainty in your prediction. This can be a huge advantage when making decisions based on these predictions, like deciding how to size an investment. Second, GPs can be applied to a wide range of domains. This means your inputs could be weird things like variable length strings or graphs made of nodes and edges. And third, they enable very efficient hyperparameter selection, which can be a real advantage for certain problems. So hopefully that got your attention. Let's get started. Okay, let's say we're facing data like this, and our goal is to form a predictive distribution of y given x. That means I want something where if I plug in an x value, it'll give me a distribution over y. This allows me to say something like, if x is equal to this, then there's an 80% probability that y is between this and that. The important thing here is that the distribution of y depends on x. Got it? Okay, so what should we do? Well, one suggestion here is linear regression. That is, we fit a line and then estimate the remaining noise variance, which gives us a predictive distribution. The problem is, this is missing an important source of uncertainty, the uncertainty in the line itself. How might we capture this? One idea is to use Bayesian linear regression. Here's the idea. First, let's forget the data. For the sake of a notationless explanation, I'd like to use a rather visual and unusual definition of a model. It's just a useful way to think, but don't take it too literally. Okay, the definition is, a model is something that produces samples of functions before you factor in the data. In the case of Bayesian linear regression, samples look like this. We'll call these our prior samples. With these, we can use Bayes' theorem to update our model such that it produces samples that agree with our data. So, if we bring back our data and apply Bayes' theorem in the background, we'll get what we call posterior samples. Nice. All right, and how do we use these samples to actually get that predictive distribution? Well, you can apply a noise variance to each sample. Here I'm showing 1 standard deviation intervals. Then to get the final result, we just average these over many samples. Well, technically an infinite number, but we'll get to that later. Now, if we look at this, we notice something nice. The intervals get a bit wider the further away from the data you get. That's exactly how you want your uncertainties to behave, and it's a big improvement above the fixed intervals we had earlier. With that, I think we're ready to discuss GPs. Basically, the mechanics are the exact same as we just saw, with one primary generalization. That is, instead of dealing with samples over lines, we deal with samples over general functions. Though not too general, typically they're smooth functions of some kind. Okay, but this is a far more flexible model. If we had data like this, we could do our Bayesian update and still get a very nice posterior predictive fit. That is pretty damn cool. But now the question is, how do we actually control this model? How do we determine which kinds of functions are more or less likely to be sampled? Well, that is a big question. And here's where I need a little leap of faith from you. I need you to accept the following as true without really knowing why it's true. If you do that, we can make a lot of progress real quickly. Here goes. It turns out which functions are likely to be sampled are determined by something called the kernel. This is a function which measures how similar two inputs are. If the number returned is large and positive, the inputs are very similar. If it's large and negative, the inputs are very dissimilar. Also, one note here. You can't just use any function. There are technical restrictions I'm not discussing, but fortunately, most software won't let you play with invalid kernels. Moving on, let's make a few observations. First, in our example, and in fact, all examples in this video, we're using a one-dimensional input. But in general, they can be vectors. In fact, even this vector notation is a little too specific. In general, the x's could refer to any two objects. All that is necessary ultimately is that we can measure similarity between any two of them. That's how you get flexibility to new domains like variable length strings and graphs. And second, This kernel depends on this vector tau, which we can use to tune our model. These are hyperparameters. Okay, let's back up. The model comes down to which prior functions are likely to be sampled. That sampling is dictated by our kernel. So this means we need to carefully design it. That is, we need to decide what makes two x's similar. As an example, let's consider the most common kernel, called an RBF kernel, for a one-dimensional input. It's written like this, and it comes with two hyperparameters, which we'll discuss in a minute. Now, to show you the output of this kernel, I'm going to create a grid where the horizontal and vertical axes are the two kernel inputs. With that, we can visualize all possible similarities as a heat map. If we look at this, we see that the kernel gives higher values the closer you are to the diagonal. That means the kernel thinks x's that are near each other are similar. Sounds reasonable to me. And now we can ask, what sample functions does this kernel produce? Well, they look like this. Now, I know I didn't explain how exactly the kernel produces these samples, but I can describe how they relate. The idea is, the GP will sample functions with close y values for x's deemed similar by the kernel. In other words, you get similar y's for similar x's. Got it? That's important intuition, so make sure to repeat it to yourself. Similar y's for similar x's. Now, in the case of the RBF, if the x's are close in distance, then so are the y's, and that gives you these nice smooth curves. Next, we can play with those hyperparameters. This one is called the length scale, and it scales up or down the distances between x's. If I set it to a small value, most input pairs are considered different, and this means the samples can wiggle more rapidly. If it's large, all pairs are similar and the samples change much more slowly. And what about this? It's called the output scale, and it determines the scale of the y values. If you increase it, the functions span more of the y-axis. If you decrease it, the opposite would happen. Okay, let's talk more broadly. Outside of the RBF, there are many other kernels, especially once you consider multidimensional inputs. But instead of reviewing those, let's just talk about the most typical way people model with a GP. Basically, you have a set of simple kernels available to you, and you create complicated models by combining them. A very typical way to combine kernels is to just add them together. Now, that leads to a question. How do the samples of that summed kernel relate to the samples of the component kernels? Well, in the case of addition, it's simple. Adding kernels corresponds to adding sampled functions. Easy. But does this idea also work for multiplication? That is, if you multiply two kernels, can you create a sample from that by sampling from each kernel and then multiplying those sampled functions? Technically, no. But in my experience, it's a useful approximation to pretend you can. If you're curious why I think that's okay, I've included a short argument in the description. And beyond that, there are other ways to adjust a kernel, all with different impacts on the functions sampled, several of which I don't understand. But if you're curious, check out my sources. They go into plenty of detail. And if you're brave, comment on your interpretations and I may add it to the description. But with that, we have a rough way of generating complex kernels. To get a feel, let's do a quick modeling example based on toy data that you would never come across in the real world. Okay, that toy data looks like this. What I'd like to do now is show you how to think about modeling, specifically how to combine simple kernels. The first simple kernel I'd like to introduce is the linear kernel. It's written like this, and it comes with one hyper called the variance. In this example, I'm using a variance of 1/2, which gives me this similarity heat map. That heat map then implies these function samples. As you can clearly see, they all go through the origin. Just as an FYI, it's not hard to add a shift parameter that allows a non-zero y-intercept. But in this case, we don't need it. Next, let's introduce the periodic kernel, which is written like this. It has two hypers, the length scale and the period, and its heat map looks like this. As you can see, inputs that are some fixed distance apart are considered similar. That will give, as the naming suggests, periodic functions. Think of them as RBF functions that repeat after some fixed interval. Okay, so now let's revisit our data. Looking at this, it looks like we have a quadratic trend, meaning it grows like x squared. So, how might we capture that? Well, let's remember how we can think of kernel multiplication. That is, if we multiply two kernels to make a product kernel, we can think of a sample from that as the product of two functions sampled from each kernel. Okay, let's try that. Let's say our model's kernel is just two linear kernels multiplied. To imagine a sample from this, let's imagine sampling one function from one kernel and another from the other kernel. Now, if we were to multiply these two functions, we could think of that as a sample from the product kernel. Kind of. Again, this isn't technically true, but it's helpful for modeling to pretend it is. So, if we were to actually sample from the product kernel, we get samples like these, which look very similar to the multiplied function we just saw. And looking at this, it should be clear that some of these could fit our trend. Okay, next, we just need to add in the periodic kernel. In the case of addition, adding kernels corresponds to adding sampled functions. And unlike multiplication, that relationship holds exactly. So if we add in the periodic kernel, then our model would produce samples like these. Looking at these and our data, it's not hard to imagine that one of these might match our data. From here, the posterior samples look real good. In fact, they look too good. Toy data totally makes modeling look easy. Also, this picture is extra rosy because I used the right hyperparameters from the beginning. In real applications, you need to optimize for those. We'll discuss that later. But the message still holds. Combining kernels can yield a really nice posterior predictive fit. My intention is that modeling feels like layering on effects, and we speak of those effects in terms of similarities. So hopefully that gave you a taste of the modeling game. But if you want to actually model this way, you'll need to at least smell the math. Fair warning, this will involve some linear algebra and statistics. If you're unfamiliar, watch anyway, because, well, of course I'd recommend that, but also because I've included graphics which should help you skate around the notation. So let's get into it. As always, let's start with our data. We have n observations of an input vector x and an output number y. In this case, let's assume that the y's have been demeaned to have mean 0. Next, our task is to provide predictive distributions for m test inputs. Make sense? Hopefully this setup looks familiar. A lot of ML models start with a similar problem statement. Now, let's get into GPs. Let's assume our y's are noisy observations of some true function f of x. One note here, the variance of the noise counts as another hyperparameter of our model. Next, let's discuss notation. Let's collect everything into matrices and vectors. Capital X is a matrix where each row is a vector input. Capital X star is the same thing, but for the test points. The bold-faced Y is a vector of all our observed outputs. The bold-faced Fs refer to the unobserved true function outputs for all our inputs. Okay, next, let's say K sub XX is an n by n matrix containing all kernel similarities for any two inputs from our data. Also, similarly define these related matrices referring to test point similarities. Got it? I just threw a lot of notation at you, so it may help to pause the video and digest this. Especially since we're about to reveal the major GP assumption. This is where things get interesting. Okay, we assume that our observations and the true function outputs at our test points are jointly distributed as an n plus m dimensional multivariate normal. Now, before I show you the details, let's recognize that this is weird. In most cases, when we assume a distribution, our data gives us many observations of it. In this case, since this is an n plus m dimensional normal, then our entire data set counts only as a partial observation of one sample from this thing. That is an alien idea, and it should totally bother you. But, in fact, these aliens are brilliant. Okay, so now I should show you the details. We write it like this. What this is saying is, paste together our observed y vector and the unobserved true function output at our test points into a long vector. Now, we assume that this thing is distributed as a multivariate normal with mean 0 and a special covariance matrix. That covariance matrix is then made up of our kernel similarities between all inputs. By the way, this is block matrix notation. So this whole thing is n plus m by n plus m. And this is n by m. Got it? Also, there is one tweak. For the submatrix that governs only y, we add the noise variance to the diagonal. This is how the noise variance finds its way into our model. I'll show how it impacts predictions in a bit. Now, again, this is from a different galaxy. Declaring that a covariance matrix is just the similarities of x's is very different from how other models think. But it works. It has the effect, as we mentioned earlier, similar x's will yield similar y's, which is kind of a smoothing assumption. And that idea is actually pretty common in ML. Okay, next we should ask, how do we actually factor in the data? Well, this is where the normal distribution really shines. Basically, if a vector is normally distributed and we observe it partially, then there is a well-known mathematical result which tells us the distribution over the unobserved elements given the observed ones. This is the Bayesian updating we referenced earlier. Specifically, given our data and our test inputs, the distribution over the true function vector is another multivariate normal. The mean vector is given by this, and the covariance is given by this. To feel what's happening, let's explore conditioning in a ridiculously simple case. The case where we have one observation and one test point, which we'll plot along the horizontal and vertical axes. Now, our GP assumption says that these two will be governed by a mean zero multivariate normal. The shape of this distribution is governed by the inputs and the kernel, which I'm not showing here. Now, let's say our observed y turns out to be 2.5. Now, given that, what should the distribution of f be? Well, looking at this, it should be the 1D distribution we get when we slice this 2D distribution. In particular, it gives us this distribution for f. So that's all this expression is doing. It's slicing, but it worked with higher dimensions. Still, let's not be ungrateful. The fact is, this is only easy because we are using the normal. In general, slicing a distribution like this can be an expensive, sometimes impossible calculation. Anyway, at this point, it's a good idea to ask something else. What happens if the kernel deems the x's to be very similar? Well, that would give you a high correlation. As you can see, the observed y and the f prediction have moved closer. My hope is that this makes it feel okay to use similarities as covariances. Okay, with that, let's back up and connect this to what I showed earlier. The GP assumption gives us our prior samples. Each function comes from drawing a sample from the normal. Here, I'm using an RBF kernel. Now, let's say we have some data. Well, to get the posterior samples, we just sample according to the normal after conditioning. Finally, this also gives us the posterior predictive distribution. Just make sure you factor in the noise variance. If you're curious about the details, check this note out. And as promised, I should mention the impact of the noise variance. Basically, if the noise variance is high, your model will ignore the data. If it's very low, the model will interpolate the data, which means it takes it very literally. But there are other hyperparameters as well. This is what happens when you vary the length scale, and this is what happens when you vary the output scale. Looks kind of cool, right? But this begs the question, how do we actually choose our hyperparameters? Well, for that, we need to cover one last topic, hyperparameter selection. Let me tell you, if you make it through this, you can claim you're a GP expert because you watched one whole YouTube video on it. If someone says that doesn't count, you can say, no, I finished it, it was like 20 minutes. And then they will walk away, which is fine. That conversation wasn't going your way anyway. Okay, let's stay focused. Remember, our hyperparameters are the tau vector, which determines how the kernel measures similarity, and the noise variance. The idea is to select those which maximize the log likelihood of y after integrating out possible functions. It means we're optimizing this, which, given our assumptions, turns out to be this integral. Now, don't worry about interpreting this equation directly. Let me just show you what it's calculating visually, and then it'll be easy to see why this thing is worth optimizing. First, let's say we have this data, and we're using a GP with an RBF kernel. That comes with three hyperparameters: the length scale, the output scale, and the noise variance. As you can see, I've chosen some values arbitrarily. Our goal is to pick the best ones. Now, let's sample a function f from the prior. prior. Next, we ask, how well does this sample explain our data? Well, if we drew these lines, we could use these to form this value. We do that by passing each into a mean zero normal with our noise variance, and then take the product of all those. I would plot that, but it's an extremely small value, so I won't. Just think that this value depends on how much red you see. Now the goal is to pick the hyperparameters that do well over an infinite number of samples. If we change the hyperparameters, the average amount of red may improve. It may not look obvious, but trust me, the average amount of red you see can be improved by changing the hyperparameters. So this is how we choose hypers. Intuitively, we're saying pick the hyperparameters where the prior samples explain the data best. In other words, pick a model which will sample functions which will agree with your data without actually seeing the data. I think that makes sense. But now, here's the convenient thing. We don't actually need to generate an infinite number of samples. The normal distribution allows us to calculate it exactly with only a little algebra. In fact, it turns out to be equal to this. It's just the log density of the y vector according to some multivariate normal. That is a major luxury. Now, this term breaks down further, which is useful to know if you actually want to run this optimization. But that's a level of detail I'd like to gloss over. Instead, I'd like to point out one important fact. We can calculate the gradient of this value with respect to the hyperparameters. That is a big deal. Ultimately, it means GPs allow you to optimize a lot more hypers than would otherwise be possible. Okay, by this point, I've sold GPs pretty hard. It's about time I reveal some of their drawbacks just to be balanced. First, calculating the posterior involves inverting the n by n kernel matrix, an operation that scales like n cubed. In other words, it scales like a mom and pop shop. Fortunately, there is a lot of research and software designed to bring that cost way down. Second, designing GPs is very much an art. In my experience, they don't work super well right out of the box. Often the functions learned may be too smooth or too wiggly, or learning hyperparameters may just be tricky. So you'll need patience and a willingness to learn to wield this tool. Third, depending on your kernel, they have the potential to break down in higher dimensions. If you're using something like an RBF kernel, that's akin to doing a nearest neighbors algorithm, which doesn't work well in high dimensions. All things considered, when uncertainty is important and you have a solid understanding of what you're trying to model, then GPs are a solid choice. Also, I'd like to end by pointing to some resources. I personally am merely a GP enthusiast, and this video is only the tip of the iceberg. There is an ocean of research applying GPs to spatial statistics, time series forecasting, and experimental design. Also, there are efforts to remove much of the art of GPs by using neural networks to learn the kernel automatically. Finally, there's pretty mature software to offer this type of functionality. My personal favorite is gPyTorch. If you're comfortable with PyTorch, I'd recommend that. The developers have gone to great lengths to reduce the computational cost. In fact, reading through their docs is a great way to get familiar with GPs. I'll include all these resources in the description. If you're going to apply GPs, exploring those is a must. With that, there's only one last thing to say. Thank you for your focus.